Okay, here's a step-by-step video tutorial on the Arduino software. I've downloaded the software already and I've already installed it. It should download and install to a folder on the documents directory. Once you have that downloaded, what you'll do is you'll open Preferences. And right here, this is the board manager box that it talks about in the Blackboard information. You'll paste what's in that document into this box. What that does is you can see it links the software to a website. It's a GitHub website, GitHub user, and it's got board definitions for the Plduino and also for the ESP8266 package that's inside the controller. So if you get that, say OK. Then you'll open Tools, Board, and Board Manager. And you'll see at the very bottom a couple of new items. Go ahead and install the 1.2 software for each one of these. Okay, it takes a few minutes to do that. Once you've done that, it might ask you if you want to update the board definitions, and you'll say yes. Okay. What it's doing is it's already got some pre-installed boards. All of the Arduino cards are pre-installed. So as they update board definitions, they'll ask if you want to update, and you may as well. Okay. So right now, when I go to Tools and Board, you'll notice that I have pre-selected the Arduino 2560, Mega 2560, because that's what I have in front of me here. I do not have the Plduino. If I did, I would select this option right here, Plduino / Mega 2560. And what I'm going to do is I've already also downloaded a template program, and let me open that now. I'll say File, Open. This happens to be it right here, standard layout. So when you open that, you'll see this file pop up. I typed in lots of comments in this file, so you have some reading material. / indicates a comment, indicates that a comment follows. There's a link here to the overall website. Const means a constant value. Int means integer. Also on this website, there's a reference folder that describes all of the functions in the software. So you'll want to normally you want to open that as a tab and keep it open while you're working, so you can go back to the reference, because sometimes you forget the syntax. Is there a question mark, a colon, a comma, details. The software is very particular, of course. When you compile your program, if you don't have everything just right, you'll get error messages. So it's normal, but you'd like to minimize that if you can. Okay, so here there's some description about what this really does. It says the term relay 1 is equivalent to the number 2. That's what it says, that equals number 2. However, in the program, you'll use the word relay 1, and the compiler will substitute the number 2. So we like to define words as numbers, so that we don't have to use the numbers. We can use the term instead. So you see there's one here for an LED, an onboard LED, speakers, real-time clocks. The LCD screen is on here. The touch screen is also on there. So what they've done is they've added all these peripherals to the Mega card, and they basically are defining where the pin numbers are. Which pins are they using? So we need this template in order for the Plduino to operate correctly, because it's been pre-configured to operate this way. The only exception to that are there's some digital outputs. Digital outputs are open collector transistors. So that means that you'll connect the load to plus 24, let's say, and the other side, which would normally go to ground, you'll connect to that open transistor, the open collector. And so when that output turns on, let's say it's output 38, the transistor will ground the load and make it turn on. So it's a low side switch that turns on connected loads. Okay, so we also have some digital inputs. Digital inputs are opto-isolated, so they can, they'll accept 24 volts in. The whole Plduino, the whole reason we purchased that was because it's got a more of an industrial feel to it. You can bring in 24 volt control signals, and you can generate whatever voltage you need through the relays on the outputs. So it's better from the standpoint of not having to work at the component level to connect interface chips and all the related components for that. It simplifies interfacing the system into something larger. So that's why we're using it. Okay, so there's also, well, I didn't list them on here, but there are also analog inputs. So we can feed in voltages, and they are predefined on the board. For some reason, I didn't put them in here, but we can always do that later. So here's where it gets interesting, I suppose. We're trying to use a state programming method for the work that we do. So what I did was I predefined 5 different state values, thinking ahead, because it is possible that we have parallel processes running in the program. So they're not technically running in parallel, because the system still executes just one program at a time. But within that program, I could have different systems, each one in a different state. So to make it as flexible as possible, I just typed in 5 different states, A, B, C, D, and E, and we could easily come back and add more. It's not a problem. The only problem we run into is just running out of memory, and that could happen at some point. So here's the setup instruction, the setup function. What we're doing here is defining the direction of the pins. So DN is an input, Dout is an output, and I've also got the relays. Relays are outputs as well. Go back up a little bit. So in this function, in this routine, I have an instruction called digital write. What that does is turn off the onboard LED so that it's not lit. And then just below that, I basically turn on that LED. So I turn it off and I make sure it's on. That pin, that LED is actually connected to a pulse width modulated output. So the instruction analog write, what it does is it creates a dimming effect of that LED. So 200 means it's not full brightness, but it's bright. You can see it. So all this does right here, it says it turns on the LED so you know it is running. It's always good to know that the software is executing, and if it's running, at least we know that it's possibly working correctly, because the LED lights up under program control instead of just being tied to the power connection. Okay, right here there's an instruction called serial.begin, or serial. There's a a data monitor screen that works through the USB cable. So when I execute this command, I can click right here. There's a little button called serial monitor. When I do that, I get a screen that pops up, and that screen can display data from the program. So it can send out messages or values, whatever I want to send to the screen. So that I open that just because we'll need it as we go along, and it's a good time to go ahead and talk about it. Okay, so below that we have the main loop, or the loop, and this is where everything happens. So just to get into a routine of doing it this way, we use the switch case structure. What that does is it looks at the variable known as state A. So let's say we have state A and it's equal to 0. Okay, if it is equal to 0, if that is the case, we execute the instructions after the colon, but before the break. So anything I type in here, I will execute. So what we want to do is we want to run instructions, but we would prefer not to try and branch away from this case. So what I mean by that is I don't want to say, go to or change something and make it leave this case. Like there's a go to instruction. Go to instruction branches the program control to some other location. And that interrupts the flow of things. And in this case, we don't want to do that. So what I would do is I would execute some instructions here. And the last thing I would do is say state A equals, let's say, 100. So it will break from what it was doing. It will come down to the bottom of the entire uh, loop function. And then it will come back and check state A one more time. And it will see that it's 100, and it will skip over the case 0 instructions and do the case 100 instructions. So we want to put instructions here in the case that will just be executed but not cause a branch. Okay, if I want to branch from case 100, what I'll do, the last instruction, or one of the, let's say I have an if test, if something is on, change to state 200. What I do is I change the value of state A in this case, and then I finish up the logic in here. So I guess we'll have to carefully look at that and make sure it doesn't create problems. But we want to have a structured program that's not jumping around. We'd like to have like, of course, the state diagram shows a trigger from one state to the next, and we want to have an orderly flow, an orderly program flow. So we'll have to try a few things to see how that's going to work for us. Okay. Anyway, so I go down a little bit further. There's a default state. So for this structure that I'm currently looking at, let's say I have a case equal to 407. Well, there is no 407 here, so it'll execute this by default here. So it's sort of an error trap. Okay. If I go a little bit further, I do a print line instruction. All that does is send the value of state A to the serial monitor. I can see what it's doing. Okay. So after it's finished this structure here, I'll just tack on another one for state B. So I would continue to do that until I've got all the structures for all the different processes in my program. The last thing we'll have at the very bottom is this curly bracket, and it says don't delete the bracket below. If you accidentally delete that, the program won't compile correctly, and of course it won't run either. So let's do a quick verify. Verify is like a pre-test. It looks at the program and decides if it looks okay. Okay, so right now it's doing that. And you can see the error message at the bottom. There is no error. It's done. It used up a little bit of memory. Everything's good. So let's go ahead and do an upload. The lights blinked on the card a little bit and it's done. So if I press the reset button on the card, the LED that's under program control, it turns off and it turns back on. So I know it's working, at least that part of it's working. So that's a quick rundown of how our structure will work. There's something else that I meant to type in here and I just did not. The loop instruction executes from top to bottom and comes back around to the top again. So at the top of the program, like at the top of the loop, right around here somewhere, what I would like to do is read in, well, maybe I don't want to do that. Let me think for 1 second. I was going to say that we would read in the conditions of the inputs and take a snapshot of them and use those snapshot values, we'll call them. Use those values throughout the program, the loop. However, if I do that, I'm not going to update the input conditions. I think it would be okay though, because it is dynamic. It's going to loop back around. Yeah, I think that's fine. Here's why I'm thinking this over and debating it. In a regular PLC, a regular programmable logic controller, this is how they operate. They take an image of the input conditions, they process the logic, then they update the output conditions, and then they come back around and do that again. So in this case, if we were to put at the very bottom, we could do all of our digital write instructions for the outputs. So we would not actually change any outputs during the flow of the program. What we would do instead would be to set or define the state or the condition of a variable that would then drive the output. So we would not have direct control over the outputs themselves here in the case structure. So let me show you an example of that. So for example, if I do a digital write, and I'll put in parentheses, I'll just put 0, comma, high. Okay, so if 0 was an output, this would turn on 0. So rather than do that, that's direct control of the outputs. Rather than do that, I would do something like this. Pin 0 equals high. Okay, and down here at the bottom, the very bottom of the program, just before the end of the program, I would say digital write 0, comma, pin. Is that what I called it? Pin, let me double check. Pin 0. Okay. Pin 0. So the difference here is that I don't update the outputs until the very end of the program. The cycle is it will loop back around at this point, go back up to the top of loop and repeat it. So by doing this, I'm not updating things on the fly. I'm going to hold off until the very end. And this is how PLCs operate. It's a very structured way of doing it. Now, if I want to do an immediate output, I could type the digital write instruction anywhere, of course, anywhere in the program, and it would immediately change the condition of the output. But I really think that it would be a good idea to get in the habit of updating outputs after the logic has been processed. The only exception to that would be if in this case 0, if I had some kind of a loop that wouldn't let it leave case 0, I just can't, right off, I can't see a value in doing that. Here's how you would handle that. Let's say you execute an instruction right here, if something something is true. You could create a bracket, an open bracket here, and then type some instructions, like x equals 7, semicolon, and then you could do like state a equals 0, semicolon. So that way, after each if test, if you want to stay in state 0, that's fine. Just make sure state uh, a equals 0. When you finally get to the break instruction and it loops back around to the top, it will find out that it's still in this state. So there's no reason to trap program execution in a case so that it cannot leave the loop and look at other cases in the program. So we don't want to trap it, because that's always sort of a bad idea, because then the program goes into a tight loop and all it's doing is processing that that one case, and it's ignoring everything else. So if I do have a system with multiple processes, that would just shut down everything else because they're not being supported. So I need to make sure that my program, that my instructions here allow it to leave that portion of the program through the break instruction, and then come back down and maybe update other processes, and then finally loop back around to the top and repeat the whole process. Okay. I know it sounds awfully complex at first because we're just starting, but it's good to have structure in place so we don't have to do it the wrong way and then come back around and do it a better way. There's always more than one way to do any kind of a programming exercise, but it's good to start out with some structure and then move forward from there. So I can't think of anything else I want to talk about. I'm going to try to leave this unaffected so that I haven't changed anything. Let me just look at it quickly here. I don't think I did make any changes. Let me make one small change though, just to show you what happens. So right here, let me find a good spot. Not there. Right here. I will say x equals 2, semicolon. And let me compile that. Uh-oh, got an error. X was not declared in this scope. I didn't define what x is. And what I want to do is define x as let's say, an integer value. And the place to do that is probably at the very top up here. Okay. But below the hardware definition. So right around here is a good spot. I'll do an int x equals 0. So I don't put constant in front of that because I need this to be a variable. So if I do an int x, that means x is an integer. So when I go back and compile again, it should say everything's fine. If I do an upload, everything's fine. So I'm uploading to the Mega card by itself. I don't have all the add-on components to make it a Plduino, but the controller is the same. So all of these definitions will go into that controller. So now, if I was to run this, let's do something here. So right here, instead of state A, I'm going to have it print X. Okay, and let's upload that again. And I'm going to open the serial monitor so you can see it operate. You can see the number 2 there because X is equal to 2. And this is what the serial monitor is good for. It will display values generated by this software. So it's like having a little screen that you can look at. Okay. So I'll close that. I'll get rid of that right there. I'll put it back to state A. Let me go up and delete that instruction. I don't really want to do that. I will save it and I'm going to upload it. So you might be used to downloads, like in the PLC world. Typically we download to a processor, but here we're doing an upload. So it's uploaded again, and I'm kind of at a stopping point. So we've talked about updating the board manager URL definitions. So once you do that, you update the board manager. Once you've done that, you are ready, so you can open the template and make adjustments to it. Okay, so with the template open, you are ready to take your state diagram and maybe generate some variable names or whatever you need to do. Like I can leave the x. I can leave int equals x equals 0. I can leave that in there. Doesn't hurt anything. I always need a few variables, like for counters or some odd function. So x, y, z is good. So we could do another variable definition here. We could say int y equals 0. So there's x, y. How about z as well? X, Y, Z. So when I verify that, of course, it'll be fine. I'll go ahead and save it, and I'll go ahead and upload it as well. So you notice that I'm only using 1% of the program storage space. With all this information that's in there, it's got 253 kilobytes, which just doesn't seem like a lot in the world. We talk about gigabytes these days, but 253 kilobytes is a lot of program space, as long as I'm not doing really complex things like, I don't know what it would be. You can pack an awful lot into these programs. Um, if I'm handling pictures or audio, that's where the SD card comes in. So I'm not using program space for that. That's just memory. Um, I suppose if I have a lot of variables or maybe some arrays, I'll use up some of that memory pretty quickly. Or if I have lots of libraries, like support other uh, peripherals that I'm bringing in, I have to use memory to support that as well. So anyway, so that's a quick start. And the next thing would be to try to use this template to create a program that follows the state diagram completely. And that'll be our next exercise.